So today we want to continue our discussion of sequences, series, and power series. In particular, we're looking at how to determine if a given series converges or diverges. So far, we've talked about the three big things. We've talked about the limit of the terms. If the limit of the terms of a series is not equal to 0, then the series diverges. We've talked about the integral test and the important result of the integral test, P series. We combine P series with the comparison tests, and that gives us an easy way to determine if a series whose terms are a rational or a radical function converges or diverges very quickly. So these two together mean that now it's easy to determine if a series with rational or radical terms converges or diverges. So we have covered a lot of ground with just these two tools, the P series and the comparison test. All right. Today we want to look at a new big category, a geometric series. So I want to look at geometric series. Geometric series, the terms are going to look like exponential functions. So we got rational, radical. Now we're looking at exponential functions. So the terms look like an exponential function. So a geometric series, the terms look like an exponential function. So your basic geometric series will look like the sum as n goes from 0 to infinity of a times r to the n, where we have a times r to the 0 plus a times r to the first plus a times r squared plus a times r to the third, and so on. A series with this form is called a geometric series. So I want to refer to the parts of a geometric series. I'm going to refer to A as the coefficient. So A will be called the coefficient, and R is going to be called the common ratio. One thing I want to point out is that the coefficient is going to be distinct from the first term. We'll also want, when in our calculations, we're going to want to refer to the first term. Note that the coefficient is not necessarily the first term. So an important thing to note here. So the coefficient is not necessarily the first term. Usually when we're talking about series, we just care about whether the series converges or diverges. We don't care about the sum. Geometric series is going to be different. We're going to be able to calculate the sum of a geometric series. That's why we like them so much. But since we are calculating the sum, we're going to first have to determine if we have convergence, and that happens on the infinity side of things. But since we're actually finding the sum, it's going to make a difference what's going on at the beginning. So for geometric series, that's really we have to make a distinction between the coefficient a and the first term of the series. So for example, if I build a series that says the sum as n goes from 3 to infinity of 5 times 0.98 to the n. I had to come up with a number, and I got stumped for a second there. 5 is the coefficient, and 0.98 is the common ratio. So we would say that r is equal to 0.98. A is equal to 5. That's the coefficient. But the first term of the series is going to be 5 times 0.98 to the third. So the first term of this series is 5 times 0.98 to the third. And then 5 times 0.98 to the fourth. And 5 times 0.98 to the fifth, and so on. So the first term of this series is 5 times 0.98 to the third. Not just the 5. So we want to make sure that that we make that distinction. So one way we can deal with geometric series is to use the integral test. We can integrate exponential functions. So let's try that first. It's kind of the only tool that we have in the toolbox. The only thing that would be useful in comparison would be another geometric series, but we're trying to learn about geometric series. We don't know what's going on in the geometric series. So let's start with the integral test and see what happens. If I have a series, n goes from 0 to infinity of a times r to the n, we can determine if this converges or diverges. I'm about to shove everything off my table. There we go. We can determine if the series converges or diverges by looking at an improper integral. So let's integrate from 1 to infinity a times r to the n. I should change it to an x. It looks weird. Dx. So to do this, we're going to have to replace our infinity with a limit, because that's how we plug in infinity. Oops. We don't plug in infinity. This is how we plug in infinity. So the variable is the exponent, so we're integrating an exponential function. So we're still going to have the limit as b goes to infinity because we have not taken the limit yet. Nothing has gone to infinity yet. We're just finding an antiderivative. The antiderivative of a times r to the x is a times r to the x divided by the natural log of r. Then we evaluate from 1 to b. So this will still be the limit as b goes to infinity of a times r to the b over the natural log of r minus a times r to the first over the natural log of r. And so now the value of this limit, or whether or not this limit exists, depends on the value of r. If r is greater than 1 in absolute value, then this term with r to the b will go to infinity. So this limit does not exist if r is greater than 1 in absolute value. However, if r is between 0 and 1, then the term with the r to the b will go to 0. And so the limit will be a times r to the first. The limit will convert, the improper integral will converge. So therefore, the series converges. So this either goes to infinity if the absolute value of r is greater than 1. Focus on the r to the b part. Or goes to a times r to the first over natural log of r, some constant, if r is between 0 and 1. So the improper integral converges when r is between 0 and 1, and diverges otherwise. So therefore, the series converges if r is between 0 and 1, and diverges otherwise. This was kind of lazy of me. The reason that I used it, just put a generic constant instead of writing out what the actual value is that this actual value is not relevant to our interests at the moment. So, yes, go ahead.
I was just going to ask, the ln that's the derivative for r of x, r raised to the x power?
The derivative, no, the antiderivative of r to the x is r to the x divided by the natural log of r.
Okay, got it. Thank you.
This is when we take the derivative of r to the x, the derivative of r to the x is r to the x times the natural log of r. So going the other direction, we'll divide by the natural log of r. Natural log of r is just a constant.
Got it. Thank you.
All right. No, that's a good question because we have to remember where's r. When I write things like this, I should have done 5 and the 0.98. Then x is clearly the variable, but I wanted to do an infinite number of problems all at once. So we have to remember that x is the variable, so it's an exponential function because that's where the variable is. So it's not r. R is just a number. A is just r is a constant. A is a constant. So natural log of r is a constant as well.
Got it. Thank you.
You're welcome. All right. So now we can determine if a geometric series converges just by looking at it. So the series a times r to the n converges if r is between 0 and 1, and diverges if r is greater than 1. So now we have another class of series, and we can determine if it converges or diverges just by looking at it. So for example, the series that we had before, This series converges since the common ratio is 0.98, which is less than 1. And greater than 0. Just by looking at it. Geometric series, because the n is the exponents, the common ratio is less than 1, so this series converges. And if we have a series, say, as n goes from 10 to infinity of I need to come up with numbers and I'm drawing a blank, like 3 times 1.08 to the n. This series diverges because 1.08 is greater than 1. So we have geometric series. We can determine if they converge or diverge. The fun part is that we can get more out of a geometric series. Geometric series are so well behaved that we can actually find the sum. This is not something that we always get to do when we're looking at convergence of series. Sometimes the best, all that we could get is there is a finite sum. And then someone asks us, well, what is the finite sum? So I don't know, ask some computer to calculate what it is. Get the first million terms, and that'll be pretty close to the sum. Which is like a very mathematician thing. Mathematicians sometimes they go, sometimes just all we get is like, well, there is an answer. What is the answer? I don't know, but there is one, which is the first big step. I mean, if you're looking to answer a question, if you can prove that there is not an answer to your question, that's good progress. All right. So we can actually calculate the sum of a geometric series. So to find the sum of a geometric series, we're going to start by looking at a finite geometric series. So I'm just going to write down the first n term. I'm going to write down n. It's going to be n plus 1 terms. I'm going to write down the first n terms of a series. Oh, dang. If I want n terms, I don't get to use n for my index. I want n terms. So I'm going to start the counting at 0. Another very mathematician thing to do. Start the counting at 0. So the first term is a. The next term is a time. I'm glad stuff like this gets recorded. Someday I'm going to learn to edit and make it look like I don't do this kind of stuff all the time in class. All that just switching index just like that really threw a wrench into the works. I really should have just written down, let's write down n terms. A plus a times r to the first plus a times r squared plus a times r to the third, and go all the way out to a times r to the n minus 1. The reason that we are going to n minus 1, the reason that we're going to n minus 1 is I want there to be n terms. So it's 1, 2, 3, 4 n terms. All the best programming language are zero indexed as well. Yeah, start your counting at 0. Just get used to that. If you're going to be in math, put your calculator in radians, start counting at 0. I don't know if it's still true, but if you're a computer science major, a math minor is like 2 classes away. It's just like, that's it. If you like do a couple extra classes, you can have a math minor. I don't know if that's still true. But at one point I was like, oh, maybe I should do computer science. And then I remembered, oh yeah, there's computers involved. Yeah. So the important thing to look at here is that there are n terms. Even though the last exponent is n minus 1, we started the counting at 0. So there are n terms. This is a normal thing. I'm not being weird here. We all do this kind of thing. We'll start the indexing at 0. Really what math, a lot of times what math comes down to is learning how to write things in this weird way. Math has this very strange written language. But everything else is, that's how numbers work. That's the reason for all math. That's how numbers work. So we're going to suppose that this, we're going to recognize that since we have a finite number of terms, let's let the sum of this finite geometric series be S. So let's let the sum of the finite geometric series be S, capital S for sum. We know that it has a finite sum because it's a finite number of terms. So this is not dependent upon the value of R. We're not looking at infinite series. We're going to start with a finite series, and then we're going to expand it to an infinite series. So there's a limit as n goes to infinity in your future. So we know that there's a finite sum because there's a finite number of terms. We could say the series is convergent, but that's just kind of being extra because it's a finite series. So now we're going to do some algebra. So we're going to hit this with the algebra stick for a little bit. I got to show you that my sleeves are rolled up to indicate that there is nothing up my sleeves. And let's do some algebra trickery. I'm going to take this series, I'm going to multiply by S. Oh, sorry, not by S. I said S because I was pointing at S. But that trick never works. Rawr. I'm going to multiply everything by R. So I'm going to have AR plus AR squared plus AR to the third plus AR to the fourth plus, and now have AR to the n. Now I still have n terms because this indexing starts at 1 now. Not really the indexing, the counting starts at 1. But there are still n terms. So since this is all just some finite sum, if I multiply this side of the equation by r, I will multiply this side of the equation by r as well. So over here, the sum after we multiply by r will be s times r. Now we are going to subtract the two series, the S series and the SR series. So next up, we're going to subtract the series. I want to take S and subtract the SR. I'm going to subtract the second series from the first series. So S has the terms A plus AR plus AR squared all the way out to AR to the n minus 1. And from this, we are subtracting our SR series, AR to the first plus AR squared plus all the way out to AR to the n. And what happens is that most of the terms cancel out. The only terms that don't cancel are A and AR to the n. So now there's a mass cancellation of terms. AR cancels AR. AR squared cancels AR squared. AR to the n minus 1 cancels with the AR to the n minus 1 that would have been right there that I didn't write because I was running out of space. And the only thing that's left over is A and the AR to the n. So S minus SR is A minus AR to the n. So we subtract the series, we get massive cancellation. Now we got to remember what we're looking for. What we can do at this point is solve for S, which is the sum of that original series, and it will only be in terms of A, the coefficient, R, the common ratio, and N, the number of terms. So we can solve for S as A times 1 minus R to the N, factor an A out of the numerator, factor an S out of the left-hand side, and then divide by 1 minus R. So here is a formula for the sum of a finite geometric series. This is an important sum. This is a sum of a finite geometric series. And for this sum, it doesn't matter what R is. This is useful for any value of R. So here's a formula for the sum of a finite geometric series. This is an important piece of information to have. This could be used. This is actually useful in modeling things. For example, if I was going to say put a certain amount of money into an account every month that increases by some percentage that gets multiplied by 1 plus that percent over 100 every month, then I can, for a certain number of deposits, I can calculate how much we'll have at the end. We can estimate how much we'll have at the end. So for example, So for the first time this whole class, I think we have something useful. We have the sum of a finite geometric series. The sum as n goes from 0, as I goes from 0 to n of a times r to the I, that's n minus 1, n terms, is going to be a times 1 minus r to the n over 1 minus r. So notice that here a is standing in as the first term. So if I goes from 3 to 10, then we have to count the number of terms and make sure that we have our first term. So we have to reframe things so that it goes from 0 to n minus 1. Count the terms, make sure you get the first term. This is useful. What if we, let's suppose we deposit $20 into an account each month. Into an account that increases by, I'm just going to keep my life simple, 1% every month. I know that that's ridiculous. But it's easy to modify. Let's suppose that we deposit $20 each month into an account that increases by 1% each month. How much will we have after 10 years, 20 years, 30 years? Y'all are young, 40 years. So it's easy to stay, especially for old people, to tell young people that you should start saving money now. And then, of course, those same old people that are saying, you should start saving money now. You're like, oh, great, how much are you going to pay me for this? Less than minimum wage. We're not going to give you any money, nor are we going to create a mechanism for you to get more money, but we are going to tell you that you should start saving money. So that when you're broke, we can sit there and say, oh, well, why didn't you save any money? And you'll be like, oh, well, why didn't you provide me an opportunity to get some more money? And then we'll have this whole situation where no one really understands capitalism. So we're only going to be putting in $20 a month. That's going to be our coefficient. And it's increasing by 1%. So our common ratio will be 1.01. So A is going to be 20. Let's identify our parts. Our common ratio is going to come from this, increases by 1% each month. After 10 years, that's going to be determine our number of terms. That'll be 120 months. After 20 years, we'll have 240 months, and so on.
Professor, I have a quick question.
Yeah.
Where did the 1 minus r come from? Where you're dividing it?
The 1 minus r came from the left side where I had s minus sr, and we factored out the s, and that left s times 1 minus r, and then I divided by the 1 minus r.
Got it. Thank you. Much appreciated.
No problem. I was running out of space. That's why I didn't write that. So that was kind of cheap on being cheap on my on the space thing. So if we want to calculate the sum, we can start with 20 is our first term. we'll start with 20 times 1 minus r, which is 1.01. The 1.01 is going to be raised to the 120 power. And we divide by 1 minus the 1.01. I wrote the 20. I should have been in the light blue. All right. So it's important to get the 1.01 to the 120. It's r to the 120, not 1 minus r to the 120. So I got to make sure we get our parentheses in the right place. So we get 20 times 1 minus 1.01 to the 120. That's where we close the numerator and then divide by the 1 minus 1.01, which I could have simplified, but it's too early. So $4,600.77. And then for 240, we do the same thing. So for 10 years, let's write it this way, 4,677. I'm going to do the same calculation for 20 years, 30 years, and 40 years. Since it's all the same, I'm just going to go back and edit the 120 to be 240. So that's 19,785. And 11. And then we'll go back for 360. 69, 899, 28. And then for 40, 235, 295, 45. Now, if we think about the amount that we the amount that we started with, this was just 20 bucks a month for 10 years. So the starting, if we just take the 20 times the 120, this is the amount that we put in. So 20 times 120, I'm not going to be able to multiply these, which is kind of embarrassing, but that's all right. So that's turning our $2,400 into $4,600. Seems pretty good. But then we start seeing the power of the exponential function. 20 times 240 is 4,800. I'm going to risk it and not use the calculator. And so after 20 years, our $4,800 has turned into $19,000, almost $20,000. After 30 years, our $20 per month for 360 months is going to be 6012. So $7,200 is now nearly $70,000. And what we're seeing is a competition between a linear function over here, the money that we're putting in, and an exponential function over here. Well, geometric growth over here. Where $9,600 has become $235,000. Took 40 years, but it's still just 20 bucks a month. Also, we're growing by an awful lot. To make my life simple, I used 1% per month. That's 12.7% per year. It might be hard to find that. I'm not even sure. But things are easy to adjust. If we decrease the rate, we can change our 1.01. If I cut this in half, and say 1.005. We can cut the rate in half. Let's suppose that instead of doing that, we do a linear thing. Notice the 220 is just sitting out in front. So if we increase that by a factor of 10, but that's way more expensive. And 0.005 is pretty small. 0.005, so 0.5% per month for 12 months is 6.2% per year. The important thing to recognize is the amount that you're putting away, that's one thing. The rate that you're getting, you're not going to have a lot of choice in that, depending on your tolerance for risk, which is just like how much you like to gamble. The important thing to note is how things progress over time. The important thing to note is that going up to 40, that's starting at 20, starting at 30, starting at 40, starting at 50. Starting at 50, it's barely worth it to do such small amounts. Starting at 50, you're going to have to dump a lot of money into this account every month because you don't have time on your side. Starting off at 20, look at the tiny amounts that we can put away. Any questions? Comments? So here we're talking about the sum of a finite geometric series. When we want to talk about the sum of an infinite geometric series, that's going to depend on the value of r. And if we have an infinite geometric series, we'll just send we'll send n to infinity. If r is less than 1, then 1 minus r to the n goes to 0. And so the sum of a convergent infinite geometric series is a over 1 minus r. So if I have an infinite geometric series, if n is going from 0 to infinity, the r to the n goes to 0. And so we just get 1 divided by 1 minus 0.98, 250. Infinite number of terms add up to 250. Any questions? Comments? Deep thoughts? Snide remarks? One of my favorite things is how much apps cost and how like $5 for it. If you see an app in the App Store and it's like $5, like, oh, I'm not spending $5 on an app. I want free apps. And then we forget that we're paying like $1,000 for the phone. But then again, if you're paying $1,000 for a phone, I think it's kind of ridiculous to be like spending $5 on an app. It's like, oh, come on, man. What is this, a Porsche? And I'm buying options? All right. That's going to do it for today. We have a new class of series that we can determine. We have added to our list of series, to our, where was it? There it is. To our comparison tests to use with p-series, we have added geometric series. So tomorrow it's going to start off with this list sum function, and we'll have 4 things on our list. All right, that's it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.